Espero a Juan para empezar. Sí. Es que no lo veo aquí.
Porque igual está en la otra pantalla.
Espera que no lo veo, estoy minimizando. No me sale. Espera.
No, no se ha parecido. Lo ha quitado para intentar cerrar esto.
Pero es que no me sale esto aquí.
Pero tiene que estar.
O sea, lo veo que está aquí, pero no.
Tiene que hacer stop share y luego.
Sí.
O sea, esto está aquí. Esto es lo que te estaba diciendo. Ostras. Esto es lo que te estaba diciendo. Que movieras el ratón más allá de la pantalla. No lo ves aquí.
Vale. Es como una pantalla externa esto. Vale.
Just for 1 second. You don't show up.
Ahora ya puedes poner el.
I just another new.
Vale.
Creo que estabas allí.
Vale.
Y ahora si le das al zoom, ¿volvería?
Al PowerPoint, ¿no? Al Zoom.
No, ¿dónde estabas? O sea, ¿cómo has quitado la
Así.
presentación?
Pero no estoy compartiendo pantalla ahora. ¿O sí?
¿Has dejado de compartir
Sí.
pantalla?
No.
Aquí dice que estás compartiendo.
Entonces vamos a ver, vete para allá con el ratón y vamos a intentar darle ahí a zoom, a ver si ese es el problema.
¿Aquí?
O a PowerPoint. ¿No? ¿Pero cómo has salido?
Es que le tengo que presentar de aquí.
Ahora sí.
Vale. Vale.
Okay.
Empiezo ya.
Thank you very much for being here. And today we will have the presentation of Carlos Celma, who has been summer fellow here, and he will give us a brief talk of the project he has been developing during these 2 months. So, whenever you want.
Okay.
Go ahead.
Thanks for the introduction, Juan. I am, as Juan has introduced me, I'm Carlos Celma, and I have been working with Alejandro and Juan for these 2 months in the summer fellowship, which is about the reduction of emission galaxies in the local universe. And I've been working in data that was acquired at the INT in La Palma. Okay, so the galaxies that we are working with are galaxies with strong emission lines. That these types of galaxies have been detected from the 1960s for different from different surveys, and they are strongly star-forming galaxies in our nearby universe. So these galaxies are characterized because they are compact, blue, and low mass, between 10 to the 8 and 10 to the 9 solar masses. And these galaxies are analog to an object called Greenpeace, with redshift around 0.3. And also, these galaxies are interesting to study because they provide us similar conditions as the reionization era of the galaxies. And this was an important survey that has detected this type of objects is J+, that Alejandro has made a paper last year. Okay, so J+ is at the Observatorio de Javalambre, and it's a wide multiband photometric survey. And it has 12 filters, 7 narrow, medium, and 5 broad. And there have been detected 462 galaxies by using this filter, the J. One moment, because you can see. No, okay. Vale, sí, no, vale.
En amarilla.
No, pero mejor poner online.
Okay, so yeah, the J plus, the galaxies were detected using the J0515 filter. Okay, so the data that I've been working with was acquired by Alejandro and some by Alejandro and others by the super astronomers of the INT as they were in service mode. And the INT telescope is in La Palma. It was originally inaugurated in 1967 in the UK, but then after some years it was moved to La Palma, specifically in Roque de los Muchachos Observatory in 1981. Currently, it has two main instruments: IDS for spectrography and wide field camera for photometry. But there are sometimes that there are other visitor instruments, for example, sodium profilers or stuff that also have time there. It's my mirror. The mirror is 2.54 meters. Okay. So the IDS is the instrument of the INT that we were using to acquire our data, and it is mounted at the Cassegrain focus. The Cassegrain focus is here below the telescope, as you may know, and this instrument has 16 available gratings. Depending on the resolution that you need to use, you choose one or other. For our purpose to study this type of galaxies, we chose R400B using the wavelength range between 3,600 and 6,900 angstroms. This initial setup, gave us a resolution of 1.4 angstroms per pixel. Here I show the efficiencies of some of the gratings that were closer than the one that we were using. Okay, so the data was acquired by Alejandro Lumbreras in some of the nights. Also, some of the nights was taken in service mode by the super astronomers. I was one of the super astronomers then in 2021. Here you have a photo of the 2021 INT super astronomers. And okay, so here we have the nights and the galaxies that we observed each night. So that were a total of 7 nights and a total of 55 galaxies at the end. For each galaxy, we took 3 frames of 1,200 seconds exposure and 2 arcs per galaxy. That's because of while you are exposing, the telescope is moving and flexing. So taking several arcs allows you to correct better the flexion and the movement of the lines through the arc. And also we have 1 standard per night to flux calibration. Okay, so the data reduction process that I have followed is a very systematic procedure for all observations. So the steps are doing the bias, the flood, the removing the cosmic rays, then doing the wavelength calibration, and then extract the spectra. Also, there is a correction called dark correction, but here at the INT and professional telescope is not needed because we cool the instrument using liquid nitrogen. So it's not this dark correction that is the current that is in dark is like negligible compared to the other effects. So here we are filling with nitrogen. This is not for IDS, but the other instrument, the wide field camera, because as you may notice, it's in the prime focus, not in the Cassegrain. So, all of this has the purpose of characterize the different lines of emission of the galaxies and try to obtain physical properties such as density or temperature. And for this project, we have mostly used IRAF and Python. Okay, so the first correction, I will focus now in all the steps that I have been applying to the images. So the first correction is to remove the zero level, which is known as bias, from the CCD. And at the beginning, we had some, we noticed that there were some problems with the bias, that the bias level was fluctuating during the night. So we used the overscan, which is has a similar, which is basically the same. That is the region that the detector reads, but is not physically there. So that gives you the zero level of the electronics. And for this, we have used the IRAD CCD proc task. And here you can see here, this is the original image. Here's the bias removed image. And you cannot see by eye, but it has like 2,500 counts less, which is not appreciable here. Okay. So the next step is to apply the flat. The meaning of the flat is to correct the sensitivities of the pixels. So the idea is that maybe you have some pixels that are more or less sensitive than the others. So you illuminate using a tungsten lamp the area of the observation. And by doing this, you get like this sensitivity effect. So at the beginning, we took like several flats. Then we combine them to obtain a uniform one. And also after this, the tungsten lamp has more emission in in some range of wavelengths than others. So we need to adjust a polynomial to its spectra and divide by it to obtain like this, which is the illumination corrected flat. And this gives us like the profile of sensitivities. And usually this, for example, is all the flats are normalized to 1. 1 is like the normal sensitivity. For example, if one pixel is less sensitive, it should be 0.9 or 0.8. So when you do the division, it corrects this effect of sensitivity. This has been applied to the images by IRAF using InCombine to combine all the flats to the final one, and IMARIF to perform the division. And here you can see the original image and the flat corrected one. As previous, you cannot see this effect by eye, but it's there. Then we need to remove the cosmic rays. So the cosmic rays are an effect that appear and need to be corrected. So we used Python script, this one, Bandoku 2001. And you can see that we have this script and we have a parameter that we regulate in order to choose the aggressivity of the program while removing these cosmic rays. For example, we chose that everything, okay, so the parameter looks for pixels that have very like not a smooth PCF, like very abrupt PCF, that's the typical PCF that cosmic ray has. And when you apply this program, you choose the value of the background that is above to determine that this is a cosmic ray and is not background fluctuation. So, for example, in our case, we have chosen that everything greater than 2.5 sigma of the fluctuation of the background level was considered as a cosmic ray. And we applied this to the all science images. You can see this, the initial one, the white dots that are cosmic rays, and then the final one, the final image. Okay, for the wavelength calibration, we, as I said before, we took several arcs during the night, and we, using iRAF, we opened these arcs, and we identify these lines. So we have this picture that is provided with the INT manual. So we go there and try to look for similarities and start identifying the lines. And the program makes a polynomial fit that adjusts this pixel to wavelength calibration. That's the thing that we want when we do wavelength calibration. And this is done by identify, as I said, to identify manually the lines, then pre-identifies the program automatically. The lines that we have not detected, we enter a text document that with all the last, and the program chooses the ones that have not been identified and tries to look for them in the arc. Then we do the fit coords. Fit coords is like if the program fits two polynomials, one in the x direction and one in the y, to perform the 2D transform wavelength calibration. And then we apply this with transform. So you enter the image that you want to calibrate, you enter the arc, and it gives the image the coordinates that have been fitted to the arc to do the wavelength calibration. Okay. After this, when we have finished the wavelength calibration, we need to extract the spectra. This is useful. This is needed because you need to remove the sky of the spectra, and this is done. We have used a task in iRAF, and this is done by selecting an aperture that contains our spectra and a background label that are these lines. So the program automatically collapses and extracts the spectrum and subtracts the sky. Okay, so this is an example of what it looks after this step. So in blue, there is the spectrum lines, one of the galaxies that was observed. And with orange, there is the lines of the sky, and you can see that the lines of the sky are very weak compared to the galaxy. So we have put a zoom here to clarify it a bit. Okay. So after this, that we have the spectra all calibrated and extracted, we proceed by fitting a Gaussian to some of these lines. So the idea of fitting a Gaussian is first to determine the redshift of the object. And okay, for this purpose, we have used all three 5007 line because it's the one with the more intense. So it's the brightest one. So we choose this line and we fit the Gaussian. So the spectra here is blue. The Gaussian is fitted as in orange. And because of the spectral resolution, the Gaussian overlaps the spectra here. Also, there is also here a polynomial of grade 1 that fits the background, which is these two black lines. That also is useful to is needed to obtain the fluxes that we will do now. So for obtaining the fluxes, we want to integrate the area that these lines have, and we want to do this to derive after physical properties such as temperature and density. So for doing this, we can we can integrate the Gaussian, either integrate the Gaussian that is fitting the line, or by numerical integration, integrate the line itself. But it will give similar results. Okay. So, for example, for the temperature, we have used these 3 lines that were detected. So the oxygen 3, these 3 lines. So the thing is that for temperature, for lines starting and finishing at different level of energy, the temperature is dominant. So here, okay, we have done this for 2 examples that are these 2 black points, and this is like a prediction of what this ratio should look like, and this is we can see that our points are on this curve. We have also, we show here for 3 different densities, but they look the same, so they overlap, and you cannot distinguish one from each other. So as I was saying, here, for example, these lines finish at different hyperthin levels. So this is the thing that determines that the temperature is dominant here and not, for example, the density. Okay. So for the density, the idea is similar. We use sulfur doublet, and this ratio of lines gives us the information. So for example, here, the lines that start and finish at the same level of energy, the temperature is not relevant and the density remains the density effect. So as before, we have used the same 2 objects and plotted there. We have done, one is around, has a density around 100, but this is like, this area is very flat, so this is like an upper limit, because it could be like 80 or 60, because this is very flat and difficult to adjust here in this area. And also we had this one, which is in this linear area that is more sensible to the density changes. So also we consider three temperatures here and plot the three lines for these 3 temperatures. Okay. So the conclusion is that the reduction has been completed successfully for the galaxies that have been acquired. All the candidates have been confirmed to start forming galaxies with very bright lines. And we have determined the density, as I was showing in the previous plots, between these values. And we have also a temperature range estimation of the targets. And we think that these values of density correspond to a diffuse gas that is a porous medium. And the thing where it was higher temperature in one of the cases than in the other. We think that in that type of galaxies, they are very hot because they are dominant by young and high stars, high mass stars that ionize and heat up all the medium there. Okay, so that was my presentation. Sorry? Yeah, it is a slit, yeah. I think just the center. It's fine. I mean, the slit I think was narrow to not. So I think just looking for the center, it's fine.
It's the center and the whole galaxy.
Yeah. Well, if you can fit all, yeah, yes.
They are very compact. So very small. Yeah, in general, most of them is just the same. There were a couple, I don't know if I don't think they were in the examples, I don't know, that were a bit elongated, but very little.
And for the Gaussian fits to the lines, did you see a single Gaussian or multiple Gaussian?
Here, so there is only, so we have this, for this, the idea is that we want to run the integration of the line, and our code fits only a simple Gaussian. Maybe if you use two and use a combination, maybe you get a better fit, but for our purpose and because of the spectral resolution, using one was enough. So it was 1.5, 1.4, I have it here, 1.4 Armstrong per pixel, yeah.
One is enough, no?
Yeah, one.
Yeah, one is enough because the lines are in these galaxies, the lines are very narrow, and the width is the instrumental width, essentially. So it does not include and we don't see, at least in these examples, we don't see winds or something like that. There might be in some of the others, but not in the examples that we showed.
And for even if there were some winds, that would be interesting, but for the flux, for the total flux and the ratio, that it probably doesn't change. I mean, if there are winds, there will be a very low level. I think there was some very slight in one of these, but really like way within the errors for the total flux.
Yeah.
But yeah, that would be.
Let's check the residuals after the fitting. So because then you can see from the residuals if you have such cases.
That's interesting for different scientific results beyond this.
More questions?
So the sample are 55 galaxies. What are the plans for the others?
Sorry?
What are the plans for the other galaxies?
So for the, you said because I have only showed two, and okay, so the thing is that I run out of time while doing this, and I only had time for doing two of them. But in the future, we are planning to do. Maybe I can start a final thesis master about this topic, so I can finish the others and try to do it better. The things to correct things, and yeah, try to.
The others have also reduced, but the flux measurements, we only have time for these examples.
How automatic is this?
So the thing is that you said the reduction of the fitting of the reduction. Okay, so I mean there is not. Yeah, we are using IRAF, and it's not like fully automatic, but yeah, we try to do some list of the images, and for example, the overscan is subtracted immediately with the list. But then, for example, the wavelength calibration is not automatic. You need to go there and look for the different lines, identify. So yeah, some of the steps are more automatic and others less.
These questions, wavelength calibration can be complex.
Any other question? No? I thank again, Carlos.
Ya puede, voy a parar la grabación.
Vale.
No, pues más bien dominando, tomando los datos que habían tenido.